Chapter 1. Introduction. Signals are all around us, carrying information in various forms. Think of the sound waves from a musical instrument, the voltage in a telephone wire, or the light waves that allow us to see. Signal processing is the art and science of extracting, manipulating, and interpreting the information carried by these signals. We can do this with analog circuits, but digital signal processing, DSP, offers many advantages. By converting analog signals into a stream of numbers, we can use powerful computers and algorithms to perform complex operations that would be difficult or impossible with analog hardware. This allows for more accurate, reliable, and flexible systems. For example, with DSP, we can remove noise from a recording, enhance a blurry image, or compress a song into a small MP3 file without losing too much quality. Chapter 2. Discrete-Time Signals and Systems. In the world of DSP, we work with discrete-time signals, which are sequences of numbers that represent a signal at specific points in time. Imagine taking snapshots of a continuous signal at regular intervals. That's essentially what a discrete-time signal is. These signals can be classified in various ways. For instance, a signal can be finite or infinite in duration, and its values can be continuous or discrete. We also have systems, which are processes that take an input signal and produce an output signal. A particularly important class of systems is the linear time-invariant system. Linear means that if you scale the input signal by a certain amount, the output signal is scaled by the same amount. And if you add two input signals together, the output is the sum of the individual outputs. Time-invariant means that if you shift the input signal in time, the output signal is shifted by the same amount. LTI systems are fundamental to DSP because they are easy to analyze and design, and they can be used to model a wide range of real-world phenomena. Chapter 3. The Z-transform and its application to the analysis of LTI systems. The Z-transform is a mathematical tool that allows us to analyze discrete-time signals and systems in a different domain, much like the Laplace transform is used for continuous-time signals. It converts a discrete-time signal, which is a sequence of numbers, into a function of a complex variable, z. This transformation is incredibly useful because it can turn complex operations like convolution, which is used to describe the output of an LTI system, into simple multiplication. This makes it much easier to analyze and design LTI systems. By finding the Z-transform of a system's impulse response, the output of the system when the input is a single pulse, we can determine its properties, such as its stability and frequency response. The inverse Z-transform allows us to go back from the Z domain to the time domain, so we can see how the system will behave in the real world. Chapter 4. Frequency Analysis of Signals and Systems. Frequency analysis is the process of breaking down a signal into its constituent frequencies. Think of a musical chord. It's made up of several different notes, each with its own frequency. Frequency analysis allows us to identify those individual notes. The main tool for this is the Fourier transform. For periodic signals, signals that repeat themselves over and over, we use the Fourier series, which represents the signal as a sum of sine and cosine waves at different frequencies. For non-periodic signals, we use the Fourier transform, which represents the signal as a continuous spectrum of frequencies. The power density spectrum is a way of visualizing the spectrum, showing how much power the signal has at each frequency. This is incredibly useful for a wide range of applications, such as identifying the frequency components of a sound, analyzing the vibrations in a mechanical system, or designing filters to remove unwanted frequencies from a signal. Chapter 5. The Discrete Fourier Transform, Its Properties and Applications. The Discrete Fourier Transform, DFT, is a version of the Fourier transform that can be computed on a computer. Since computers can only work with a finite number of data points, the DFT takes a finite length sequence of a discrete time signal and calculates its frequency components at a set of discrete frequencies. The DFT has many important properties that make it a powerful tool for DSP. For example, it is a linear transformation, and there is a direct relationship between the DFT of a signal and the DFT of a time-shifted version of that signal. The DFT has numerous applications, including filtering, spectral analysis, and convolution. The fast Fourier transform, FFT, is an efficient algorithm for computing the DFT, and it is one of the most important algorithms in all of DSP. Chapter 6: Efficient Computation of the DFT, Fast Fourier Algorithms. The fast Fourier transform, FFT, is a family of algorithms that can compute the DFT much more efficiently than by direct calculation. While a direct calculation of the DFT would take a number of operations proportional to n squared, where n is the number of data points, the FFT can do it in a number of operations proportional to n times log n. This is a huge difference, especially for large values of n. There are many different FFT algorithms, but they are all based on the principle of breaking down the DFT into smaller DFTs. The Goertzel algorithm is another efficient method for computing the DFT, but it is optimized for calculating only a single frequency component, making it useful in applications like touch-tone telephone dialing detection. Chapter 7: Implementation of Discrete-Time Systems. Once we have designed a discrete-time system, we need to implement it in hardware or software. This chapter explores various structures for implementing these systems. The direct form structure is the most straightforward, but it can be sensitive to numerical errors. The cascade form structure breaks down the system into a series of smaller, second-order systems, which can be more robust. The lattice structure is another popular choice, known for its good numerical properties. When we implement these systems on a computer, we have to use finite precision arithmetic, which means that we can only represent numbers with a limited number of bits. This can lead to errors, such as quantization noise and coefficient quantization errors. It's important to understand these effects and to choose an implementation structure that minimizes their impact. That's all for this episode of Geek Capsule. We hope it gave you a fresh perspective on the world of technology. We'd love to hear your thoughts, so feel free to leave a comment or share your feedback. If you enjoyed the show, don't forget to subscribe and join us next time for another essential read. Until then, keep your curiosity sparked and your mind open.